Hello, welcome to our lightning testing webinar. Thank you for joining us today. This webinar is being given by MET Laboratories. MET is a leader in the testing of electrical and electronic equipment for environmental hardiness, product safety, and electromagnetic compatibility. MET operates world-class labs in Baltimore, Maryland, Santa Clara and Union City, California, Austin, Texas, and also runs operations in China, Taiwan, Korea, and Italy. This webinar will run about 30 minutes with an additional 15 minutes for questions and answers. Due to the number of registrants, all attendees will have their phones muted. If you have a question, please type it in the questions area of your control panel. We will attempt to answer all questions at the end. If you are having technical difficulties, you can contact us the same way or call us at 410-935-6053. That's 410-935-6053, and we will try to resolve it quickly. Just a quick note on other upcoming events. In July, MET is hosting an EMC design and troubleshooting seminar in Fremont, California. And in September, we are hosting our annual Global Product Compliance Seminar and Crab Feast in Baltimore, Maryland. You can register for these events at www.metlabs.com. Today's webinar is being presented by Asad Bajwa. Asad is Director of MET's EMC Lab. At this point, I will hand over the presentation to Asad.
Thank you, Banavi. Hello, everyone. Today we're going to talk about Section 22 of RTCA DO-160, which basically covers the indirect lightning induced transient susceptibility. We will talk about how the lightning phenomena happens, what kind of problems the electronic product can run into, and then we will look at the specifics of the test methodology and how these testings are performed and what are the different criteria and the requirements by DO-160 and other organizations. A brief outline of my presentation. I'll start with the introducing how the lightning phenomena happens. We'll jump straight into DO-160, Section 22. We look at the requirements, and then we talk about the test methods, and towards the very end, we can take a few questions. DO-160, the latest rev at the moment is Rev G. DO-160 covers whole bunch of different aspects of the environmental and electromagnetic compatibility aspect of the electronic products. From Section 16 all the way up to Section 25 is primarily the electromagnetic compatibility discussion, various different test methods. There is some overlap with the other similar specs by the European Union. There is some overlap with on some of the requirements with 461. The primary focus today is the Section 22, which is indirect lightning, and the Committee 135 from DO-160 is responsible committee which maintains the requirement related to the lightning. Lightning is not only required by the aircraft manufacturers, also the Federal Aviation Authority specifically requests this particular test method when there are assemblies or sub-assemblies which are supposed to go into the commercial electronics. Before we continue, just few references there and how over the years different revisions of DO-160 came out. Not too long ago, DO-160 Rev D was being used. Then we saw Rev E coming out in 2004, and then Rev F came in 2010, and Rev G is already out. And the hope is that with the Rev G, we won't see a significant earlier revision before next 5 years. Before we jump into lightning and how this phenomena happens and how the tests are performed to make sure the electronic products are hardened enough to handle the severe effects of the indirect lightning, let's explore what goes on a commercial aircraft. I would say a couple of decades ago, the definition of avionics we had back then is very different from what we consider avionics today. Nowadays, there are not only engine controls, servo motor controls. Basically, nowadays, anything and everything on a commercial aircraft, like anything else in the world, is going more towards electronics and electronic controls. Take the example of the landing gear, radars, Wi-Fi system, satellite TV, which we have on the aircraft for several years. They all become the essential part of a commercial aircraft, and not only it's desired that all these systems are working correctly during the normal operation. At the same time, the concerns are these systems do not contribute into the electromagnetic spectrum by generating RF energy, which could lead to the problems. Wi-Fi, for example, is relatively a new addition. A few years back, nobody thought the Wi-Fi access points will be considered as avionics, but now with the reliability of with the smartphones and people's reliability on the smartphones, people's desire to be accessible and to be connected to their offices and workplaces makes these things more and more desirable to be on the commercial aircraft. Now, that said, let's look at where DO-160 comes into, where other organizations come into play, and what is the trend going forward. And we will talk in the next few slides what's being proposed for the DO-160 obviously covers the commercial aircraft. What's being proposed by the Department of Defense as far as MIL Standard 461 is concerned? Excuse me. So we already talked about that RTCA DO-160 Committee 135 is responsible for Section 22, which is basically indirect lightning phenomena. However, the maintenance of this Section 22 has been subletted to Society of Automotive Engineers Committee AE2, which makes sure the lightning requirements are up to date. Similarly, the Section 23, which is the direct lightning effect, is also covered by the subcommittee AE2. At this point, I just want to make a slight distinction because between Section 22 and Section 23, Section 22 is the indirect lightning effect, whereas Section 23 covers the direct lightning effect. The direct lightning effect, as the name specifies, is when the lightning hits directly onto an electronic subassembly or the component. Then the thought is not to see the functionality. The thought for Section 23, which is the direct lightning, the idea is to see the survivability of how much the electronics would survive, or would the electronics assemblies or sub-assemblies will be able to withstand that kind of lightning. Would there be any fire? Would there be any shattering of the component? The concern more is from the safety aspect. Whereas with the indirect lightning, primarily the thought there is to see when the indirect lightning phenomena happens, which travels onto different parts of the aircraft, commercial aircraft, which can eventually reach to the different electronic sub-assemblies or controls within a commercial aircraft. How would that affect the functionality of the overall system? So that's the slight distinction between Section 22 and Section 23. Similar to the requirements by DO-160, which are basically adopted by FAA for all the commercial aircraft. FAA requires the manufacturers to follow DO-160 primarily to ensure they can withstand the lightning threat when the commercial aircraft is being flown. The European organization, EuroCAD, has a publication ED-84, which is practically, as far as the lightning is concerned, it's practically the same specification as DO-160, section 22. Now, let's look at, I mentioned earlier that the trend there is that the 461 will be adopting the lightning requirements as time passes by. So in next few slides, we will explore why the thought there is to adopt the lightning requirements into 461. But what I want to mention is that at the moment, the Rev F is the latest revision from MIL Standard 461. Per the last meeting which took place at recently of the subcommittee who is working on the new Rev of the 461, which will be G, the discussions were such that it clearly indicates that the thought is to incorporate the indirect lightning phenomena in addition to some other tests like ESD, which are primarily covered by 464, into Rev G of MIL Standard 461. If that happens, from that point on, not only the commercial aircraft manufacturer, also the military programs, Air Force, Navy programs, for the aircraft applications, a manufacturer would be required to perform the lightning testing according to basically section 24, which is indirect lightning testing. The current information is that the draft version of 461G will be released by late 2013, and a final draft, once it's approved, will be released early 2014. Now, section 22, the indirect lightning. Let's see who would need this testing. All the airframe manufacturers, I have listed very many countries, and some of the manufacturers, primarily one of the bigger, I will just say few of the bigger names, like Boeing or Raytheon or Cessna or Airbus, so on and so forth. There are many more manufacturers out there. So point I'm trying to make is that for everybody who is either one of these manufacturers or the folks who are supplying electronic subassemblies to these manufacturers who will be putting the planes together or aircraft together, they will all be required to perform the lightning testing according to section 22. Now, the question obviously comes to mind, why lightning is gaining more interest today compared to 5 or 10 years ago? The answer is fairly simple. With the development of the composite materials, with the popularity of the composite materials, because of the ease of the manufacturing, because of the convenience of fabricating different parts of the aircrafts, primarily with the composite materials, they are gaining wide popularity. Not only the commercial aircrafts, to some extent, many of the Air Force, Navy, or Army applications, the aircraft manufacturers are using more and more the composite material into the manufacturing. Now, the concern with that is with the metallic structure of the aircraft, it inherently provides shielding. It inherently provides protection against many of the threats which come from the electromagnetic environment, primarily from the lightning. Because a complete metal-to-metal connection will act as in ideal environment, will act as a shield, which will basically deter any electromagnetic phenomena and try to protect the electronics inside from those electromagnetic phenomena like the lightning. However, with the usage of the composite material by definition do not have any conductivity, thereby they are wide open to the electromagnetic phenomena. And magnetic energy, for electromagnetic energy, these composite materials are just transparent, and the RF energy goes straight through without any losses or without any loss of the strength of the electromagnetic field there. So that on one side provides convenience of the manufacturing, but on the flip side, that opens a huge floodgate where it creates a whole bunch of different electromagnetic problem as far as the susceptibility is concerned for the aircraft manufacturer. So there are various techniques how to handle that. The topic today is not to go into that, how to address the effect of the composite material and how to provide additional shielding there. The point I'm trying to make is that due to the use of more and more composite material, now it becomes a lot more critical that the commercial aircraft components are very thoroughly tested for the phenomena like indirect lightning to ensure all electronic components and avionics on board can survive should the lightning phenomena happens. My next slide pretty much talks about the same thing with a little bit more detail. It kind of shows what parts of the aircrafts are generally used, what the trend is in the industry today, where people are using more and more composite materials out there. Now let's go straight into the testing requirements, which is covered by section 22. This slide is basically an overview of or summary of what is the requirement set forth by section 22. I will repeat some of that just to explain a little bit more. There are altogether 7 test waveforms. Test levels go from 1 to 5, and in some of the next slides we will talk a little bit more about these waveforms, and we'll talk about what these test levels are and which level, what's the comparison between level 1 versus level 5, in what cases testing is done to level 5 versus level 1. That said, level 5 is the worst case level, and level 1 is the least stringent level, and we'll talk a little bit more about that in the next few slides. Then there are 2 different kinds of test types. There's a pin injection, cable bundle. There are 3 test methods: direct cable induction, ground injection. Then there are 3 different applications: single stroke, multi-stroke, multi-burst. I also want to briefly describe test category designation, because this question comes very often. Typically in any test program, when we get a test plan from the manufacturers or the FAA, they would generally describe the lightning levels and requirements by a 6-digit test category designator according to Rev F or G. The first letter, which will be A or B, that indicates the pin injection test. And when we say letter A or B, that would indicate a waveform set. It could be 1, 2, 3, 4 or 2, 3, 4. Just giving you an example. So basically, the letter A or B will refer to a waveform set in section 22, and the number after the first letter is the level requested by the requesting authority. So in this particular case, B3 would mean waveform set in table B and test level 3. The following letter would indicate the waveform set G for cable bundle test, and the corresponding letter afterwards would be the test level, which is 4 in this case. And similarly, the next one is the multi-burst, the waveform set, and the test level for multi-burst. Then finally, the standard talks about the test requirements, the test procedure, how the pin injection and or cable bundle tests are performed. So let's go through the remainder of the presentation to see what these waveforms are and how could they potentially impact an electronic product in question. So just a summary of the waveforms. There are 7 waveforms, and in the next few slides, we will talk about what they are, what's the rise time, fall time. Some of them are the current waveforms, some of them are the voltage waveforms. So the very first waveform, which is referred as 1, is the current waveform. It's a double exponent, Rise time is 6.4 microsecond. Fall time is 69 microsecond, which is basically from maximum peak to the 50% decay point. This is a current waveform, which is typically applied using a current clamp and or another coupling method for pin injection testing. Waveform 2 is a voltage waveform. It's an extremely fast rise time waveform, 100 nanosecond rise time, and decay is 6.4. The interesting thing is the fall time is not defined to the 50% point. The fall time is defined up to the zero crossing of the voltage wave. The waveform 3 is very similar to the waveforms defined for MIL standard 461 CS116 testing. However, CS116 talks about a whole bunch of different waveforms. Here, there are only two frequencies, 1 megahertz and 10 megahertz. And the Q factor is slightly different from the Q factor defined for MIL standard 461 CS116 test. The following waveform 4 is also a voltage waveform, goes from 6.4 to 69 microsecond. Waveform 5A and B, both are the current waveforms. Rise time 40 microsecond to 120. The other one is 50 to 500 microsecond. Waveform 6 is also relatively very fast rise time waveform. The rise time is 250 nanosecond, and the fall time to 50% point is 4 microseconds. Now, that was just the description of the waveform. Now, the question comes to mind is why there are different rise and fall times required. Without going into specific detail, the simple answer is that over the years, people collected the statistical data based on the lightning strikes happening to different electronic components, avionics, and others. And based on the collection of the statistical data, they saw these waveforms occurring more frequently than the others. And based on the statistical data, standard writers picked these waveforms because they occur a lot more frequently than other waveforms. So these are chosen as a test method to make sure the electronic components are hardened according to these waveforms because they are the ones which happen a lot more frequently than the others. Now, test levels. As I mentioned very briefly earlier, that level 1 being the least stringent and level 5 is the most stringent of the levels. Level 1 testing will perhaps be done for a product which will be installed into a very well protected environment, meaning once the product is installed into a very well protected environment, so the threat of lightning will be already reduced because of the protection provided to a certain given environment. On the other hand, the level 5 perhaps would be used for the components which may have no specific protection or they are totally exposed. So it will be prudent to have those products tested to the worst case scenario. Similarly, level 2 and 3 would be in between the worst case and the least stringent environments, according to the location where those products or avionic component will be installed. Now let's quickly look at the different test types. In my summary or in the overview, I mentioned there are two test types: pin injection test and the cable bundle test. The pin injection test is done directly into the pins of the connector. However, majority of the time, this testing is done with the EUT powered on, which kind of makes the testing a little bit more complicated because in many cases there might be very high voltages present, and connecting the lightning onto the pins which are powered becomes very delicate procedure. So care should be taken when applying the lightning signals to the EUTs, which is powered per the test requirement. Now, to draw the contrast between the pin injection and the cable bundle testing is done obviously, but as the name states, on the cable bundles, which would be bundled according per the actual installation requirement. The cable bundle basically check the functionality of the product. In other words, the idea of the cable bundle test is that when the indirect lighting phenomena happens, what will be the level of degradation of performance for a given application of the product. However, the pin injection test, on the other hand, tests for if the lighting phenomena happen, what will be the extent of the damage. So that's a delicate contrast between these two methods. The pin injection test will check for if the lighting happens, how much will be the physical damage to the product. On the other hand, cable bundle test will assess if the device is functional, what will be the degradation of performance in a given application. This is just a summary of the three test methods we talked about. There is direct pin injection, there is a cable bundle test method, there is a ground injection test method. So for direct pin injection, only the pin injection test applies, whereas for cable induction and ground injection, either pin injection and or the cable bundle test method could be used. Here is a little bit more detail on the three cable bundle test applications. As we mentioned earlier, there is a single stroke application, there is a multi-stroke application, there is a multi-burst application. Single stroke is just a single stroke of the transient, whereas and it's applicable for all the waveforms. In the multi-stroke, multiple strikes of a transient are done with the first transient being at the highest level, and the consequent transients, which can be up to 13, will have a lower amplitude according to the specification. And the multi-stroke application covers only the waveforms 1, 2, 3, 4, 5A, and 5B. Multi-burst is only for waveform 3 and 6, where multiple bursts of the transients are injected onto the line to see how much the degradation of performance would be on in a given application. Test procedures. The test procedures basically covers the pin injection test, the cable bundle test. Considering that we are kind of running out of time here, I will briefly skip through the test procedure. This slide basically covers how much the cable needs to be raised by 50 millimeter from the ground plane, what should be the cable bundle length, at least up to 3.3 meter, what's the cable bundle length for IO lines, the power lines, so on and so forth. This particular slide talks about the power leads, how the power lead need to be organized. They run in a typical configuration. The power leads run parallel to the edge of the table. The power leads are raised by 15 millimeter at least, and at least 1 meter length of the cable is used into the test setup. And most of the time, the majority of the test plans require the looms are used for powering up the product. Just a summary of the different test procedure which we kind of covered. The pin injection basically covers the waveform 3, 4, 5A. For cable bundle, all waveforms are applicable, and the test methods for cable bundle tests are cable induction method, ground injection method. For pin injection, all the three methods could be applicable: direct injection, cable induction, and ground injection as well. I'm gonna quickly skip through this and jump straight into the waveform verification. Reason being, that's one of the more critical requirement by DO 160 section 22. For the folks who are familiar to MIL standard 461 requirements, MIL standard 461 requires verification test to be performed before each test is done. Regardless, those tests are emission testing or those tests are the immunity testing. MIL standard mandates a certain procedure to validate the test setup. Similar to that, section 22 talks about waveform verification, meaning the idea to perform this verification is to ensure that when we are talking about performing a certain waveform to one of the given levels, say level 5, the verification method will ensure that, one, the waveform meets the rise time and the fall time requirements using different kind of probes, oscilloscopes. The idea is to ensure that during the with the excess usage of the test waveform generator, the waveform and the quality of the output has not deteriorated. So before each test is performed, it's required to ensure that using different monitoring probes, current clamps, the lab will ensure that the rise time, fall time, and the test level meet the specification. So in this particular case, if I may describe, say we're talking about the waveform 1. Waveform 1 is the current waveform. So using a small loop, which can be shorted or opened using either a banana lead or some sort of switch, a current loop is generated. Using the coupling clamp, the current is injected right into the loop by induction phenomena. That will lead to the flow of the current. Then simultaneously using a voltage probe and the current probe, the parameters like the level and the rise time and fall time of the waveforms are measured. And once it's verified, the waveform parameters are correct and the level has been established, that's the only time the test technicians will take the probe out, injection probe out, and plug it into the setup for actual waveform. And if it's a cable bundle test, they will wrap the clamp around the cable bundle and inject the waveform accordingly. This is our different waveform cable bundle test. Slightly different procedure. In this particular case, listen is being used. This particular example is for basically for the physical test setup. The EUT and support equipment are connected with the cable bundle, which could be IO lines and or power hooked up together depending on a given configuration. The transient signal is injected using the injection clamp, and simultaneously using an oscilloscope with the two channels for voltage and current, the parameters, the level, the rise time, and the fall. It's ensured that the signal is being injected. By signal, I mean the transient signal is being injected to the correct level. While the transient lightning signal is being injected onto the cable bundle, the test technicians make sure they are monitoring the product for the signs of susceptibility to ensure that the product can withstand any degradation. The product can withstand the lightning signal, and there is no degradation of the performance. It's required by standard to ensure that before each indirect lightning test, especially for the cable bundle and or the ground injection test, that the manufacturer provide a certain monitoring method where the performance of the product could be clearly monitored, and it could be determined whether the product meets the performance evaluation or not. This is another waveform verification method for the ground injection, relatively similar to the cable injection method. The difference would be that in this case, the probes are being hooked up to the generator directly rather than through the monitoring clamp. Otherwise, the current is still being induced using by the generation of the small short-circuit loop, and oscilloscope is being used to measure the voltage and the current parameters of the waveform and to establish the test levels. This is the cable. This is the typical setup for the cable bundle ground injection. Now we are towards the end of this presentation. Just a very brief summary. We talked about what are the waveform requirements are. We talked about there are 7 waveforms. There are up to 5 different test levels. Then we talked about test types, test methods. We briefly touched base on the verification and test setups for 3 main test methods: direct, cable induction, ground injection, so on and so forth. We briefly looked at the test procedures, and we talked about the test category designation. At the end of my presentation, I just want to show the picture of the lightning setup we have. We have this lightning setup in our facility in Baltimore. This setup allows us to go all the way up to level 5, and it gives us the capability to do all the 7 waveforms and all the test methods we discussed during this presentation. With that, I conclude my presentation. If you folks have any questions, Barnaby has already explained the procedure to post the question. I'm going to hand the control back to Barnaby. Thank you very much. Thanks for your time. I appreciate that.
Thank you, Asad. Asad will hang around during this Q&A period. Just a quick note, a copy of this webinar will be available on our website. We will send a follow-up email with a link to this file. Now we will answer questions. If you have a question, please type it in the questions area of your control panel. For questions we can easily address now, we will read the question aloud, then give the answer. Give us a minute to get oriented with the questions, and then we will start answering them.
Okay, folks, we have started receiving some questions. The very first question is that will the same requirement in DO-160F apply to mill standard? Okay, I'm assuming the question is more as in terms of the lightning requirement of Section 22 of DO-160. So the answer is that this is still in the draft phase. And the news we are hearing from the committee who is working on the draft, the news coming from that committee is that, yes, that is indeed the case. All the 7 waveforms with the test methods will be incorporated into Rev G of the 461. Whether that happens with Rev G, whether that happens in future, we can't say. But the only thing I can say with certainty is that these discussions are taking place, and the committee is seriously considering that, adding that, and we are hoping that when the Rev G comes out, or when the draft of Rev G comes out, these requirements would already be there. I was physically, personally present in IEEE symposium last year in Long Beach, and where all these discussions were taking place, and this point was discussed in detail, and there were proposed test methods which were basically replica of what was in replica of what was in Section 22 of DO-160. There is a question. Are strike points, receptors, ever used on the aircraft to take the lightning to them and not to the other parts of the aircraft? I think the answer really lies on who the manufacturer would be and what the design technique they are using. To the best of my knowledge, I haven't seen that approach to tackle the lighting problem in the aircraft environment. There is another question about whether the Rev-G of 461 would use the same waveforms and test levels as are required by DO-160 Section 22. My response to that question would be that for the last discussion in the Long Beach, which I participated in, following up with some folks who are actively involved into the development of the draft version, the thought today is to basically copy-paste, well, in a way, probably copy-paste is oversimplification. In a way, copy-paste the requirements from DO-160 Section 22 as is into the 461G. But that is just a discussion point there. What will be the final picture? It's very difficult to say at this stage. However, I can certainly say that these discussions are actively taking place. What will be the final shape of the requirements for Rev-G? At this point, we do not have any more questions, so I will give the control back to Barnaby.
Okay, thank you, Asad. We will be participating in the EMC Symposium again this year. It's August 7th through the 9th is the expo, and the symposium actually runs all week, and it's going to be in Pittsburgh this year. MetLabs is in booth 1024. If you have any additional unanswered questions from this webinar, please contact us via phone or email or meet with us at the EMC Symposium. Tomorrow, we will send a follow-up email that will include a special offer and a link to the presentation. That concludes our webinar today. Thank you for joining us.